We're going to talk about more exponential function modeling. Today, we're going to spend a lot of our time, actually, all of our time, talking about finances and how money grows in accounts based on um, interest rates and the number of times it's compounded. So, what we learned yesterday is we learned that if we have some amount of money or some amount of things, uh, that's in an exponential growth problem equal to the principal or the amount of money that we initially started with times or amount of thing that we started with 1 plus or minus r to the x or to the t or something. So this is true in general. However, in financial situations, what ends up happening sometimes is we end up not following this model precisely because they can do other things with your money. So instead of saying that they're going to compound your money yearly, which is basically every year, they just add the amount of money into your account that is that was in there basically. What they do is they'll compound it based on how much of the money was in there in particular points in time. So they may compound it daily or something like that. So if they give you 5% interest, which is very high for any bank in this day and age, if they give you five, very, very, very high, by the way, most interest rates in banks are well under 1%, well under a fraction of a percent, actually. But let's say it's just 5%. If they say it's compounded daily, that does not mean you get 5% daily. What it means is they divide the 5% by 365. So you actually get a very small fraction of that 5%, but you get it more often. And so what ends up happening is as that compounding happens, you end up getting slightly more money in the long run if they compound it monthly or daily or something like that. The more often they compound it, the more money you get. So that's what this formula is. So um, if A was the total amount and P is the principal, that would be fine. Remember, variables, uh, the letter that it represents is not that big of a deal. But in this case, the Y is the amount of money you have. This A represents the initial amount. R, once again, represents the rate. N appears twice, so N is also in the exponent. N is the number of compoundings. So that's how often the interest rate is taken on your account within a given time period. And then T, which is right here, T represents time. Now there's one other case for this, and that is this Y equals PE to the RT case. That's what happens when N, this number of compoundings, goes off to infinity. And that's one of the reasons why E is so amazing, because when you take this function and you make N go to infinity, so basically this is basically zero because you have an infinity in the bottom, and then you're taking it to the infinity power, that basically turns into an E. It's pretty nuts. It's crazy. But the P in this case stands for the principal or the initial amount. The R is the rate, and the T is the time. So now let's do some example problems. You put $5,000 into an account that yields 5% per year. This is not compounded, so we can just use our regular formula. Y equals 5,000 times 1 plus 0.05 to the 8. Now you can use the compound interest formula. I'll write that real quick because you're compounding it once, and then to the n, which is 1 times t. So notice it doesn't really change anything. Like if I divide this by 1 and multiply that by 1, nothing changes. So it's not like it's changing anything about the problem. So I can use either formula. And I end up, after I type in the calculator, getting $7,387.28. Now you would still round to 3 decimal places, just to show that you're rounding to 3 decimal places all the time. And then after that, 0.277, sorry. And then after that, since it's a money problem, you can round to the nearest cent, but you want to put the 3 decimal places first. Okay, next problem. Suppose you put $3,000 into an account that yields 4% interest compounded monthly. So now we're definitely using compound interest here. So y equals 3,000 times 1 plus 0.04. Oh, it's compounded monthly. So we're going to divide by 12. What that basically means for you is that the 4% is, you're going to get 4% interest, but you get less than that, um, but you get it more often. So like you get 0.04 divided by 12, which is about 0.00333333. So that's like 0.33-ish% interest, but you get it 12 times. And so over the course of a year, that ends up being almost equivalent to 4%. It's actually slightly more than 4% if you just did it once. And then it's 12 times 5, because in the formula, we have 5 years and then 12 compoundings. And you type that in the calculator, and you end up getting $3,662.99. So you have, um, with this 5 years, you end up with $3,662.99. Now, what if I ask a question, when will this amount, that 3,000 that you put in the account originally, when will it equal $7,000? It's a slightly different question. So I can replace 7,000 for y. Then I have 3,000 times 1 plus 0.04 over 12 to the 12t. So now my objective is to solve this for t. So I can divide both sides by 3,000. I end up with 7/3 equals 1 plus 0.04 over 12 to the 12t. This is not a really nice number, so I'm just going to kind of leave it like that. And then what I will do is I'll take a log of both sides. So it would be log base 1 plus 0.04 over 12. Now you can simplify that if you want, but you would be rounding, and that's pretty dangerous, of 7/3 equals 12t. And then at the end, you're going to divide this whole thing by 12 to get the answer. So take log base 1 plus 0.04 over 12 of 7/3, then divide that by 12. So to answer this bonus question, when is this going to be worth $7,000? After 21.218 years. So this 3,000 turns into 7,000 with 4% interest compounded monthly after a little over 21 years. You put $10,000 into an account that yields 3% interest compounded continuously. So that's going to be PE to the RT, that formula. How long until the investment is worth 15,000? Well, um, just a quick question before that. What will be worth in 2 years? That's a pretty easy one. So Y equals 10,000. So this initial 10,000, E to the 0.03 times 2 years later. That ends up being $10,618.37. So that's not too bad. I mean, that's a relatively easy question. Um, How do we figure this one out? Well, it's very similar to that bonus question that we just did up here. So what we're going to do is we're going to replace the y with 15,000, and then p is 10,000, e to the 0.03 times t. So we have to figure out what time, how long is this going to work? So we divide by 10,000, and we end up with 3 halves times, I'm sorry, 3 halves equals 3 halves equals e to the 0.03 t. And then what we want to do is we need to take a natural log of both sides. That gets rid of the e. So we have natural log of 3 halves equals 0.03t. And then to get our final answer, we would divide by 0.03. So t equals natural log of 3 halves, or natural log of 1.5, divided by 0.03. And if I type that in the calculator, I get 13.516 years. So t equals 13.516 years. Now I have this calculator on the side of the screen just to make sure that we know how to get to e in natural log. Um, so you hit the second button, then you hit natural log, and then that will get you e to the x. So that's kind of where this one came from when I typed that in the calculator. And if you want to get natural log, you just hit the natural log button, and then that goes from there. Now, this final question, Mr. Mead is very secretive about his investment strategy. He will not tell you how much money he recently invested into the math department investment account that has an 8% interest rate compounded quarterly. How long till his money quadruples? Well, it looks like I forgot to hide the answer, so you know what the answer is before I even start. But let's take a look at how we would do this. So this is compounded quarterly. That means 4 times a year. So I have some amount of money that I'm going to have at the end. That's equal to the principal times 1 plus 0.08, 8% interest rate. It's compounded quarterly, so it's divided by 4, to the NT, so 4T. So I just subbed in 0.08 and 4. Now, I didn't tell you how much money I invested, but I want to know how much when it's quadrupled. So, well, it quadruples when the amount that was in it originally is multiplied by 4. So that means I can replace the amount at the end with the amount that I had at the beginning times 4. So then when I divide, I can divide both sides by p. The p's go away. So it doesn't even matter how much money I had in at the beginning. I'm going to end up dividing by it, and I should get 4. That means it's quadrupling. So that means it's appearing 4 times as big as it was before. So then that's equal to 1 plus 0.08 over 4 to the 4t. Now, this is actually easy to simplify. 0.08 divided by 4 is 0.02. So this is 1.02. Now I take a log of both sides. So log base 1.02 of 4 equals 4t. Then I divide both sides by 4. I get log base 1.02 of 4 divided by 4 equals t. And that's where this comes from. So it would take 17.501 years for Mr. Mead's money to quadruple.